Welcome to the MCAT Basics Podcast, brought to you by the physicians at Med School Coach. Each week, Alex Starks breaks down high-yield MCAT topics so you can score as high as possible on test day.
So today we're going to talk about the gas phase. Now, we usually don't see gases, and so our conception of it tends to be vague at best and just plain wrong at worst. So we're going to clear a few things up and make sure we're all on the same page. So if you consider a particle, and if the particle has sufficient kinetic energy, then it will exist in the gas form. And that would be after it undergoes a phase transition from either a liquid like boiling water or from sublimation, being from its solid phase. And this is what's happening when your ice cubes mysteriously disappear in the freezer. So phase transitions and all that isn't what we're going to spend our time talking about. I really want to focus more on the physical aspects of gases. So let's get to it. Physical properties of a gas. Now, a gas has no fixed volume and no fixed shape. At the macroscopic level, if the gas was colored, we could see it and we could observe how it diffuses through a room, for example. But at the microscopic level, gas particles are considered to be very far apart, and that's going to be important later. So, these particles move insanely fast and functionally independent of each other. These properties are why gases are able to expand inside a container. So, if that seems a little abstract, just recall the last time you sprayed Febreze in the bathroom or something, and what you've done, you've released a gas that was contained in a small handheld canister of a fixed volume, and then it diffuses in order to fill the volume of the entire bathroom. Okay. So we need to chat about some of the terminology and standards that are important in understanding and communicating about gases. So some of these can be dry, but they're really important not only so you can have a straight-up content-based. Fair warning, some of this can be dry, but it's important because not only can you have a straight-up content-based question about the different gas laws and whatnot, but it's also really important to gain an intuition for how and why gases behave, and that's very important. And so now the first thing I want to just kind of clear the air with is absolute temperature. And this is going to be in Kelvin. So all gas laws need to be worked using the Kelvin scale because, well, that's what scientists agreed on. So 0 Kelvin is absolute zero. And if that ever happened, then it would probably mean the universe has died and there's no entropy. Definitely no Kelvin is used in physics almost exclusively, and that 273 Kelvin is 0 degrees Celsius, and that this is a standard condition. Make note of that. Very important. Standard temperature is 273 Kelvin or 0 degrees Celsius. Now, the other standard condition to know is that pressure is defined as 1 atmosphere. That's 760 millimeters of mercury on a mercury barometer. So these two standard conditions are such that a mole of gas will fill a space of 22.4 liters. Now, you may be wondering, why is it 22.4 liters? And what's happening here is that the temperature of a gas, it provides enough kinetic energy to expand to that size, but the ambient pressure around it, that's being that 1 atmosphere, is enough to contain the molecules from diffusing to a volume that's more than 22.4 liters. Now, of course, that's not to say that a mole of gas can't be contained in a much smaller container, like that Febreze canister, for example, but we would need to monkey with the temperature or the pressure in order to do that. Now, I want to backtrack just a little bit and talk about that barometer I mentioned. And the reason why is because this concept has shown up multiple times on the WMC practice materials in both a quantitative and qualitative setting. So imagine you have a kid's swimming pool filled with mercury. And a disclaimer, this is a bad idea, just pretend, just go with it. So we've got this pool of mercury just hanging out doing its thing. Then you take a big test tube or glass canister, and then you turn it upside down and you place it in the mercury. Now, this is a special test tube because it has a valve above it that you attach a pump to, and we create a vacuum inside of that test tube. Now, what happens? Nothing, something, make a prediction real quick. All right, so the mercury is going to rise up the tube. So for our thought experiment, let's say it raises to 50% of the total tube height. That question wasn't so tough, but this one is a little more complicated. Why does it raise in the first place, and why does it stop at 50%? There's nothing magical about 50%, I just made it up. Well, it raises because the pressure of the atmosphere pushing down on the surface of mercury in the kiddie pool forces the mercury into the tube that we create a vacuum of. This is similar to the negative pressure that our lungs use to draw in air from the atmosphere. Alright, so why does it stop? Is it because we've decreased the volume of the tube, inside of the tube that is, and so the air pressure inside the tube now equals the atmospheric pressure? Well, no. We create a vacuum, remember? The reason why is simply the weight of the mercury is too much for the atmospheric pressure to push it up any higher. It's too heavy. There's not enough force being applied over that certain area. Now it's time to dig into gas laws, and we'll briefly go through the individual laws that essentially formulate the ideal gas law, because it is fair game for the MCAT, but it appears to be low yield. Again, what's most important is that you gain this intuitive sense of how gases behave. It's important to note that the gas laws we talk about pertain to ideal gases only. An ideal gas is just this imaginary gas dreamed up by scientists and students because life would be much easier if there were no intermolecular forces to complicate the simple ideal gas law. So, for ease of writing notes down if you'd like, I'll state the assumptions for an ideal gas. These are and know this, assumptions for the kinetic molecular theory of gases. Alright, so numero uno. Gases are comprised of particles with no definite volume, though they do have a defined mass. In other words, their volume is laughably small compared to the distance between themselves and other molecules, which is pretty true. Numero dos. Gas particles experience no intermolecular attractions or repulsions. So the corollary to this is that gas particles have no potential energy. They're all kinetic energy. Trace. Gas particles are in continuous random motion, and of course, if there were any intermolecular forces, then there would be non-random motion, because particles would move in response to attraction or repulsion. The fourth is that collisions between gas particles and between particles in the container are completely elastic, which just means no one is gaining or losing kinetic energy. And the last one is that the mean or average kinetic energy is identical for all gases at a given temperature, regardless of what the gas is. So an extension of this is the assumption that the kinetic energy is proportional to the temperature of a gas. Now this next part is a little mathy, but just, hang in there because it's important. So we all know that the kinetic energy of a particle is equal to 1/2 its mass times velocity squared. It's also equal to 3/2 times the Boltzmann constant times the temperature of that particle in Kelvin. The Boltzmann's constant, Kb is how we see it, is 1.381 times 10 to the negative 23rd meters squared times kilograms all over second squared times Kelvin. And of course temperature is in Kelvin, I think I mentioned that. So you don't need to memorize that constant. But what you do need to understand that because 1/2 mv squared equals 3/2 times the Boltzmann constant times the temperature, the velocity of gases can be expressed in terms of their root mean square speed. Alright, those 5 assumptions are a lot for ideal gases, but I do have a nice solution for you to help remember these intuitively. So, gases are not ideal, and they deviate from the ideal gas behavior when they're in conditions that would promote them to become a liquid due to. Now this would violate the assumptions that intermolecular forces don't exist, and that the volume of a gas particle is essentially zero. So what conditions would promote the collision of gas particles and their subsequent condensation? The first one is low temperature. So a moment ago I mentioned that the average kinetic energy is directly proportional to the temperature of a gas. And of course, if we recall that kinetic energy equation, and rightly know that mass isn't going to change, then what we're left with is temperature being directly proportional to velocity squared. So if the velocity is low because it's cold, then it's more likely that the particles will collide. So the next condition is high pressure, and this should make sense too because if the pressure is high, then the gas molecules will be confined to a smaller area, increasing the probability of a collision. Alright, so the ideal gas law is one that many of us are probably familiar with. It's going to be the pressure of the gas times the volume of the gas is going to be equal to the number of moles times the gas constant times the temperature in Kelvin, or PV, PV equals nRT. There are a bunch of component gas laws that sort of make up or contribute to the ideal gas law, and they were all discovered by a bunch of really old scientists. They're all dead, and they're hard to remember. I've always had a really terrible time remembering them, and then I stumbled upon a cool little mnemonic. They are the ABCD gas laws, so Avogadro, Boyle, Charles, and Dalton. Now something that's really important for the MCAT is to be able to quickly go from an equation or a formula with its symbols to what that means in words, because this is very much a reading test. So what I want to do is I'm going to describe the different laws in words and then give you a quiz at the end so that you can practice translating those words into an actual formula. Now, the first law that we'll talk about is Avogadro's law. That's the A part. And this states that the volume of a gas is directly proportional to the amount of gas at constant temperature and pressure. Now, the amount of a gas, you want to be careful because we're talking about moles here, not grams, anything like that. If you had to deal with this equation quantitatively, you would always need to get into moles. And this shouldn't be really hard to remember or wrap your head around because we all know Avogadro is the mole guy. Now, Boyle's describes the inverse proportional relationship between pressure and volume at a constant temperature and a fixed amount of gas. So that means we're manipulating two different variables or showing the relationship, but we're not changing that n, or the number of moles of gas. Charles' law, or I guess it would be Charles's law, describes the directly proportional relationship between the volume and temperature of a gas when the amount of gas is fixed and the pressure is held constant. The final law is Dalton's Law, and there are a couple different ways of describing Dalton's Law, but the one that I see the most often, I think it's going to be the best for the MCAT, is to state that Dalton's Law of partial pressures is the total pressure of a gas is the sum, not the product, not the quotient, the sum of the partial pressure of its component gases. So this means that if you have, a gas that's 5 atmospheres of pressure, and you have 5 gases, and you have the same number of moles of each gas, well, because of the mole fraction is equal, all of the partial pressures are also going to be equal. So we would say each gas contributes essentially 1 atmosphere of pressure. Now, what do we do if we want to deal with a real gas? Well, we have to control for the two major assumptions that affect the ideal gas law. That being, gases, the particles don't really have any actual volume in themselves, and then there are no intermolecular forces. So we do that with something called the van der Waals equation. And given the relative complexity of the equation and sort of the theory here, I would bet a lot of money that the AAMC would not actually require you to know this equation. So I'm not even going to go over it. We're just going to talk about the conceptual aspect of it. So essentially, you would take the ideal gas law, and then you have some function that would essentially handle the component that particle volume and particle intermolecular interactions would happen. So you just would take something ideal and control and adjust for these other components. So there you have it. This is pretty much everything you need to know about the physical properties and aspect of the gas phase. If you're interested, you can go to the AAMC content outline. It's what's on the MCAT 2015, and you're going to hear me reference this a lot because this is kind of like our Bible for those of us in the MCAT field. And it's going to be content category 4B. And because fluids in the circulatory system have been covered in the MCAT Basics podcast, that's why I didn't go over those. So, but if there are any follow-up questions or things that you folks would like me to expand on, just let us know, and I will make sure to do that. All right, so now on to that little quiz where we're going to practice going from the description of the different gas laws and put it into a formula. So the first one, we won't do the ideal gas law because we talked about that earlier. PIV nerd, or PV equals nRT. I love that mnemonic. So we'll start with Avogadro because he's ABCD, and we're going to recall that Avogadro was that there was a directly proportional relationship of volume with the number of moles. So we would see that as, I'll give you a second to think about it. We would see it as V1, so volume 1, over N1 would be equal to V2 over N2. Or V over N equals constant. That's another way to say it. The next one, Boyle's law, was that the pressure and the volume were inversely proportional. So the pressure of pressure 1 times the volume 1 would equal pressure 2 times volume 2, meaning at a certain pressure, the same amount of moles of gas will occupy a certain amount of volume. And at a different pressure, that same amount of moles would occupy a inversely proportional amount of volume. Next is Charles's law. I think it's Charles's law. Maybe it's Charles. I'm not sure. But this one stated that volume and temperature were directly proportional. So volume 1 over temperature 1 is volume 2 equals volume 2 over temperature 2. So as you increase the temperature of a gas, that's going to be kinetic energy essentially, and so that amount of kinetic energy is going to increase the volume of the gas. Now, Dalton's law is probably the easiest here because it's just the sum of all of the component partial pressures, and so it would just the total pressure would equal pressure 1 of gas 1 plus pressure 2 from gas 2 plus pressure 3 from gas 3, etc., etc. So that one's definitely the easiest. Now, I'm just going to take a moment as we wrap up to talk about the most important takeaways from today's episode. So if you know anything, know these things. The first one is you should understand when a gas deviates from being an ideal gas. And again, that's when any condition that would sort of encourage it to, collide, condense, and become a liquid. The next thing is the assumptions for the kinetic molecular theory of gases. Know them all. Be able to recite them. Make a flashcard. Doesn't matter. You need to know that. And I think the final one I'll leave you with is how important it is to have this really intuitive understanding that heat flow into a system will increase the average temperature of gas. And that temperature, that energy that comes into the system is going to go into the velocity of the particles. And the velocity of the particles, of course, that kinetic energy is what determines what its pressure is. All right, well, I think that's a wrap. If there is anything that you would like to see, or rather hear, in the future, please let me know, and I will be happy to oblige. Till next time.
Each episode of MCAT Basics is brought to you by Med School Coach. To access Med School Coach services, including MCAT tutoring and medical school admissions advising, visit our website at medschoolcoach.com. Good luck as you prepare for the MCAT, and we hope you tune in again next time.